In this demonstration, I am going to consider an initial value problem, which is y prime, y equals y minus t squared plus 1 with the given initial condition as y of 0 equals 0.5. And I would like to solve this problem with RK4 method. The RK4 method generates the estimate at a next point from I to I plus 1 with this equation. So it reads at yi plus 1 equal to yi, the value of y at the previous step, and plus 1 by 6 times k1, which is rk first constant, and then 2 times k2 and k3 plus k4. This generates the estimate, whereas k1 is calculated as h times, h is the step size, times the value of derivative function f at ti and yi. Then the next k is calculated as k2, and this is a calculation at half step, whereas the y value at half step is estimated. So it is ti I plus 1 by 2, and yi at the midpoint, it is estimated as yi plus k1 by 2. In Google's Colab, the facility is provided for writing the text and equations, which is compatible with the LaTeX style. So yes, this is very much correct expression. And similarly, there is going to be a calculation of K3. So K3, it comes from the t value at I plus 1 by 2 at the midpoint. However, the K, well, it was K2 plus K2 by 2. Okay. Oh yeah, that's the correct way of writing it. And it is then, sorry, this should be K1 by 2, and this should be the K2 by 2. So the value of y at the midpoint. Okay. Yes, this is extra, and therefore the expression was not converted in equation. Yes, this is correct. The t index of the function is at the midpoint, and y argument is at the midpoint. However, this is the estimation. The last one, which is K4. So it is computed as an increment at I plus 1, which is like ti plus h and yi plus k3 plus k3. Yes. So these are the k expressions. We have two increments computed at the midpoint, one increment computed from the left point, and one increment at the end of the interval. Now let's implement that in Python. So Python code, I import the libraries, import numpy as np, and import matplotlib.py.as plt. The strategy is to define the function, the derivative function, from the differential equation's right side. So as in notation, we call it f of t and y. So I keep the notation same. And over here, I have to provide a value for, I call it y prime. Y prime is equal to y minus t squared. So t times t plus 1. And then the final thing, return y prime. So this is the function definition. Yeah. It is going to generate a value of y prime from the right hand side, which is y minus t squared plus 1. And now let's write the solver. We required the initial condition. So initial condition, I call it y of 0, and this is equal to 0.5 for our problem. This is initial condition. Then I required the time interval. So I write a starting time, say 0, and the end of the interval as b, say 5. So the time span is equal to a b, from a to b, right? Well, maybe it is not, it may not be required for the solution vector. For the solution vector, I define, for solution vector, it has to be generated with a step size. So let's define a step size h, which is say 0.2. And now I generate a t vector or time vector. So time vector, it should start from 0, from value a to value b, with the step size of 0.2. So the value of times will be 0, 0.2, 0.4, and so on up to 5. So that is the vector of time interval, vector of time, and I generate this one as numpy, linear space. It requires start, stop, and number of intervals. So I use the other function, a range, numpy a range. It requires start, stop, and step. So I use from A, and to stop at B, I use B plus H, and then the step size is H, right? So with this many time values, so I calculate the number of calculations. So n vector, it is numpy size of t. For every time value, I have to generate the y estimate, the estimated value of y. Okay. Then I generate a vector. I call it y computation. So it should be of size numpy zeros, and it should be an array. There must be nv number of points, and its type should be float, right? Data type to be float. So up to this point, these are the generation of storing vectors and all the initial stuff, right? Specification of initial condition, time step, time vector generation, and the calculation vector generation, right? So for numerical techniques, we also like to generate the y. For this problem, we may have access to, we have access to analytical solution. So you can have y exact of similar size, numpy zeros, number of points, float, float, right? Number of points, this would be more n points, the number of calculations required in the algorithm, n points. Okay. So let's see whether this segment is correct or not. Okay, so we got the tick mark. which means this part is correct. And now the implementation of algorithm step by step. Okay, so we start with a value and then we move forward. So from I to I plus 1. So I write here, okay, let me first specify y computation of 0, the first value to start with, it should be the initial condition. So it is setting the initial condition. Okay, and now we are ready to move forward. Okay, so I write for I in range n points. I require n points minus 1, n minus 1 calculations, right? Where every calculation starts with the I. So I have to have the values of K1, K2, K3. So I'm writing here K1. So it should be H, it was specified earlier, times f of Ti and y computation of I, right? So with the definition of function, it will generate a value and then it will provide this value to K1, right? Then K2, it is equal to H times, okay, f of Ti plus H by 2. So this is the argument update in T, and the argument update in Y will be with the K1 by 2. So that's it. K2 calculation, then K3 calculation. This is H times f of Ti plus H by 2 and Y computation I plus this time K2 by 2. And the last K4, it is H times f of Ti plus H and Y computation of I plus plus H. No, not H. It is with the K3. So 4 Ks have been calculated, right? And then the next estimate, Y computation of I plus 1. So started from I0, this will be the first one. So I write here yi plus 1 divided by 6 times. Please don't forget to write times here, right? Computer requires a multiplication sign or equivalent to multiplication operation here. So it is then K1 plus 2 times K2 plus K3 plus K4. And then the end of this loop structure, right? So values will be generated in this vector. Okay. It seems there is some error, a typing mistake. Y is not defined somewhere. Y computation yi, right? So typing mistake. Well, okay. Yes, the problem with the indices. So I varies from 0 to n minus 1 points. So when it is n minus 1, so I plus 1 will become n points. So this is something that you have to deal as you shift from a language which starts the index from 1 to n, and a language which starts the index from 0 and go up to n minus 1. So you have to make these switches, right? So since the array, the time array T and Y computation array, they have n points where the indices starts from 0 to n minus 1. So therefore, I have to have this update, right? Yes. I correctly identified the problem. And now we are ready to see the solution. Let's see the solution, analytical solution from the nodes. Oh yes, it is t plus 1 squared minus 0.5 times e raised to the power t. T plus 1 squared minus 0.5 e raised to the power t. So why analytical? So why exact? So why exact? The first value here should be consistent with the initial condition, and here uh, I provide the analytical result. Y exact of I plus 1, it is equal to t of I plus 1 plus 1 and square of it, and square in Python should be written like this, not like this. I struggled with this problem several times because in many other languages, MATLAB, R language, the raised to the power is with the head sign. Minus 0.5, okay, 0.5 times numpy exponential function of t I plus 1. I think this is the correct expression. E raised to the power t plus 1 squared. Otherwise, I will not be allowed to stay excited. Okay, t plus 1 squared, 0.5 numpy e raised to the power like this. Okay. So now it's time to see the results graphically first. So I plot PLT, plot function with the time vector. I plot the y computation, and with the red stars. Okay. And I plot t with the y exact. Okay. And with the blue line, right? Since it is the analytical result. And PLT X label as time step, and PLT Y label as the solution y of t. And I must have legends since I'm going to plot here two curves. So the first one is y computation with RK4 method, and the other is the analytical. So behold, it's a critical moment and historical moment. I hope it is hitting many of the hearts. The numerical result is, it seems to be woven in the line, right? Like the pearls on a thread. So that's the inspiration behind this kind of interpretation, right? So pearls of numerical methods are on the thread of analytical solution. So RK4 method, the professional routine available in many of the numerical solvers. So take a deep breath, since all of you have been stunned. Therefore, take a deep breath. It calms the mind, and enjoy learning.